Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 98, the electric field. So let me just go back to where we left off, I think in the last lecture, with this principle of superposition. And so if I was interested in knowing about the forces acting on Q2, for example, and let's say these are all positively charged, you can see that there's going to be a force, we'll call it F1 acting on 1 acting on 2, directed this way. I think I want to make one of these negative, yes. Let's make this one negative, okay? So Q3 is negative. There's going to be a force vector that we can draw that is going in this direction. And that is, oops, this is the force of 3 acting on 2. Okay? Does that make sense, the way that I've drawn the arrows? And so the principle of superposition, right, tells us that we can treat the force on 3 as a linear combination, or a superposition, of the force of 1 acting on 2 plus the force of 3 acting on 2. Yes? And so if I were to write this out, I could write this as K. And then I would write, so the Coulomb constant K will be present in both F12 and F32, right? Also present in these two will be the charge Q2, right? So I can factor that out like this. And then I'm left with Q1, this is from F12, over the distance, and we'll call this distance, this vector will be R12. This vector over here will be R32. That's just a vector, the position vector, or displacement vector, from here to here and from here to here, right? So R12 quantity squared, and that will be in the R12 direction. Okay, so you see what I've done here is I've used the displacement vector between the two to create the directional portion of this vector equation, right? So that's sometimes convenient to do. Because of the charge, here I could have actually made this minus F32, since this is an attractive force, right? So minus, and this will be Q3 over R32 squared, and this is in the R32 direction. Well, this should be a hat, because it's a unit vector, it's normalized, right? Remember, if it was just the displacement vector, R32, then this would be the cube down here, okay? Yeah, so I can write that just so we see it one more time. We can also write this as K Q2 times Q1 over R12 cubed times R12, where we use the actual displacement vector. Q3 over R32 cubed times R32. Yes? Yeah. Now, if this guy has forces acting on it, what do you think it's going to do? What do you think charge 2 is going to do now that it has these forces acting on it? If you were standing here and I applied a force to you, what would happen to you? You move. You get moved, right? You're going to undergo an acceleration. Yes? And so Q2 must be undergoing an acceleration, correct? Yes. Similarly, remember Newton's third law, right? If charge 1 is acting with a force on charge 2, that means that charge 2 is also acting on charge 1 with a force in the opposite direction, and equal in magnitude, yes? Right? So this guy is going to move, correct? And so is this guy, for the same reasoning, right? So this is a bit of a dilemma, right? And I'll tell you what really becomes a dilemma in just a minute. But so when we do these kind of problems, we're really thinking, we call it electrostatics. And what we want to think of is we want to think of these charges as being clamped into position. like something's holding them there, so they're not moving, okay? Does that make sense? And our test charge, the same way. We're going to just let our test charge, just going to hold it. Like imagine you've got like a wand with a charge on the end of it, and you're sticking it down into space in some region and feeling what the force is on it. You've got some force measuring apparatus attached to this wand, and that's what you're doing, okay? We're kind of doing it we're trying to do it in a way that we don't interfere with the forces that are there. But clearly we are, because we're creating forces that weren't there before, right? Without this test charge present, right, this equal and opposite force, we call it F21 maybe, wouldn't be there, right? Now, there's a real problem when we start talking about relatively large distances or relatively high speeds, because in reality, when you put charges near each other, they start moving really fast. Right? You remember we talked about how big the electromagnetic force was? Right? These can generate tremendous accelerations, especially in tiny little charged particles, especially in electrons, which are about as tiny as you can get. And so the real problem that they undergo is the fact, remember when we talk about gravity, we talk about action at a distance, and I had said that, well, if the planet Earth was orbiting the sun, and then suddenly, God plucked the sun out of the universe all of a sudden, like, right? It would, the Earth would still orbit it for about 8 minutes, because that's how long it takes for information about the removal of the sun as a gravitational body takes to arrive at the Earth, right? And we call this action at a distance. Under Newton's system, right, he assumes it's instantaneous. So when you pluck the sun out, the Earth immediately continues on in a tangential path to its original orbit and just travels straight out into space, right? Yeah. Immediately, because he has action at a distance kind of built into it, okay? But, in gravitational systems, it's usually not much of a problem. But for charged particles, it is, okay? And so David Griffiths has an electrodynamics textbook, or electricity and magnetism textbook, in which he uses the line, electromagnetic news travels at the speed of light, okay? And that is true here. News about the position of and charge of this particle, the force, right, felt by this guy, Q2, it takes the time that light takes to travel from this point to reach it. So if we call this sometime t equals 0, right, and let's say that, so if this is t equals 0, and then we go forward in time by a little delta t, and how much forward in time? I want to go exactly R12, the magnitude of that, the distance, right, over c. If you want to make it a little bit easier, I can draw a little thing here. I'll say that this magnitude of R12 is just some x, some distance x, okay? So I like to use, when talking about speed of light stuff, I like to use feet and nanoseconds, because the speed of light in feet per nanosecond is about 1 foot per nanosecond, okay? So if these guys are separated by 1 foot, then the delta t we're talking about here is about 1 nanosecond, okay? So if we go that far into the future, right, the interesting thing is that at this new time, Q2 will not see charge 1's current position. It will see its position back in time. So if it was traveling, say, in this direction, right, it might be at some distance back here. So it sees its ghost, okay, where it used to be. Such that what we should really write for these force laws is something more like this. The F of 1 on 2 as a function of t, the time in the reference frame of our test charge, is equal to k, q1, q2. None of that changes in time, but this does change, and we'll call it, I'm just going to call it R12 as a function of t minus x over c squared, and of course with the appropriate R12 unit vector. We call this retarded time, okay? It's the time in the past at which we currently see the thing, all right? And I'll walk through an example of this, but at first you might be thinking, well, how in the heck can you ever figure this out, right? This is complicated, right? Where was it, when I see it now, right? To know where it was in the past, I have to know how far away it was then, and it gets very confusing. But let me show you one way that you can maybe shed some light on this. If you think back to special relativity, we would always draw a space-time diagram, right? Where we would draw the time axis like this, the spatial axis like this, yes? Let's assume that this coordinate system, right, what we would call our stationary coordinate system or our inertial coordinate system, is this test charge. So we're sitting here in this test charge reference frame. That means we as the test charge are always located here at 0, 0. Okay? Yes? And actually we're moving up the timeline, right? Our position is just moving straight up the t-axis here. Right? We'll call this x. Yes? But let's imagine that at t equals 0, we would be at our origin here, that we had sent out a light signal backwards in time. Okay? Do you remember how we draw light lines on here? Here c is equal to 1, so a light line is just at a 45-degree angle, and normally it would be going forward. So if I sent out a light signal forward in time, it would go out this way and this way, right? But if I send it out backwards in time, it's going to go like this. That doesn't look like a great 45-degree angle. Let me see if I can fix that a little bit better. See that? Yeah. So we're just pretending that I sent out this light signal backwards in time, okay? Now, let's introduce this particle Q1, okay? Let's just draw its space-time trajectory. What does it look like it's doing? Well, it could be doing any number of things. It could be wiggling around a bit. Something like this. Who knows what it's doing, right? But notice that it crossed this light line, this point, we'll just call it, point P, whatever, right? Now I see how I can figure out what my retarded time and retarded distances are. This, right, is my, I guess we call it T sub r for retarded time. That's how far in the past I see it. And this distance here could be the r sub r, well, I'll call it x sub r for retarded distance, okay? In our reference frame anyways, okay? So the way to think of this backwards propagate, now look at it in reality. So if at this point P, this charge sent out a little light signal, this is when it would arrive at me at t equals 0, you see? So I kind of thought about things in a silly way by thinking of sending light back in time, right, to get this point. And now you can think of it properly. At this point, charge 1 sends out a signal at the speed of light. It arrives at me at t equals 0, and that time I can get from this space-time diagram. Does that make sense? Yeah. Okay? This is a clock. This is my friend Bob. Okay? And I guess I'll be Al. Okay? Our clocks are synchronized. We're not moving with respect to each other. Okay? And we're not really thinking about special relativity here. So I'm not talking about the synchronization of clocks or anything like that. But so at t equals 0, I'm going to send out, so we can draw a little flashlight. I'm going to send out a little light signal traveling at the speed of light, okay, at t equals 0. This light signal will arrive at Bob when the clock reads this. Okay, so here I am. My clock also reads this. Maybe this was like 12, this is like 12, 15, who knows, right? Could be 0 seconds, 15 seconds, however you want to think about it. And I put my flashlight away so I don't have it. But here is when the light signal arrives at Bob, okay? And this is at time t equals, and so draw this out. This is the distance x that we're separated by. This is at t equals x over c. That's how long it took for the light signal to travel from here to here, right? And of course, we're going to give Bob a big mirror to reflect back the light, okay? Well, let's not think of it as a mirror. Let's put the mirror here. There we go. Put the mirror behind Bob and the clock, okay? So that what we're going to see when the light arrives back to us, well, how long is it going to take for the light to arrive back to us? I guess we can put the mirror behind you everywhere. How long is it going to take for this light to arrive back here? It's going to take exactly the same amount of time it took to get here, right? So this is another, this will be t equals, 2 times x over c, right? And of course that means my clock, since my clock went from here to here in that time, that means it's going to go from here to here in this time, you see? Which means his clock is always this way. And I'm getting the light signal back. I just see it. So what is it that I see, right? So by that, I'm going to draw a little eyeball, okay? What is it I'm actually seeing at this new time? I'm seeing Bob, right? And his clock reads this. Well, that must be confusing, right? Because I know my clock says this. We agreed to synchronize these clocks. So I'm actually seeing back in time. You see that? Yeah. So maybe you imagine this like a really dark room. And so the only time you can see is when you hit a light flash. You got like a light bulb. You can push the button real quick and it creates a little pulse of light that shines out, travels across the room, reflects off this mirror here. And of course the clock and Bob travels back and then you see it. And these distances are so far and so vast that it takes some appreciable amount of time. So you click the button and you're like waiting. Ah, there it is. Ah, I see. And you notice this discrepancy in the times. Okay? So you've seen into the past. Every time you look out into the stars, right, you're looking into the past. It takes time for the light from the stars that you see in the sky to travel and make their way here to your eyeballs. Well, it depends, right? You're asking like what is the maximum that you can see back? Or what the average is? Or, yeah, I mean, the stuff you can see with your naked eye, I mean, it's just years. It's a few years to maybe 10 or years or something like that. If they're really far away, they tend to get dimmer. So for stuff that's like thousands of years and millions of years back in time, you need a telescope to see it. And really you need a telescope like the Hubble telescope, or what's the new one they put out near Jupiter? All right, I'll put in the video. I think it's the James Webb telescope. These telescopes can see way back. The farthest that you can see back in time, like what we'd call like the edge of the universe, so to speak, is, as we'll learn when we get to talk a little bit about cosmology, the universe is expanding. Okay, and as you go farther away from our current position, it expands. The expansion rate velocity is receding faster. Okay, and at some point it gets to exceed the speed of light, and that's basically the edge of what you can see. Parts of the universe that from our position are moving away with a relative velocity greater than the speed of light, we can't see that because light can't make it to us, right? Yeah, so that that's probably confusing, and we'll talk about it more when we get to the cosmology section of the course. Because I said something travels faster than the speed of light, but you guys know nothing travels faster than the speed of light, right? So we have to qualify that at some point. Okay, so this makes sense, why it is you see in the past. It takes time, you want to look at something, right? So you need to see light coming from them, right? So I mean, the only way I can see is by sending this light signal. I send out this light, and then I illuminate Bob and his clock, and by the time it arrives back to me, right, it took this time, 2x over c, right? Yeah. So charges are the same way, right? They see things in the past just like you're seeing things in the past. But for them, because they're moving so fast, this effect is quite significant, okay? So what is the point of all this that I'm talking about? Well, we have a solution, how to make this problem tractable. I could write down, for example, the Feynman-Heaviside equation, which is a function of the electric field, which I haven't even defined yet, in terms of current time, but has retarded time components in it, right? But the real nice thing is we have this way of thinking about things where we can get rid of the action at a distance, okay? And so we just call it the electric field. The electric field is a condition or a state that is set up by all the charges in the space, all right? And we assume that they're all up to date, okay? So whenever we're interacting, we're no longer interacting with that charge way far away. We're interacting with the field at this point where we're currently at. So there's no need to worry about retarded time or anything like that. And as it turns out, the Maxwell's equations are sufficient to tell you everything you need to know about the electric field at that point in space. And we'll eventually get to coming up with all of the Maxwell equations, okay? More simply, right, the electric field E, which is also a vector quantity, is simply F divided by Q test. So whatever you're thinking of, your test charge, right? So you simply take the force vector. I know that looks like an E. Let me just make that look more like an F. There we go. the same Coulomb's law that we had before, and you're kind of dividing out one of the terms. So remember, Coulomb's law was like K, I'm going to say Q1. Here I'm going to just call it Q test over R1, well, I just call it R squared, R hat, right? If I just simply move this test charge over here, then I can call this E. Okay? That's a terrible E. Does that make sense? Yeah. So if I want to know what the force on my test charge is, all I need to do is multiply the electric field times my test charge in coulombs, and that will give me the force I feel there. Okay? Let me just show you the analog. We also have gravitational fields, right, when we talk about universal gravitation. So little g is defined as, we'll call it F sub g divided by m test. Okay? This is the 9.8 meters per second squared that you're used to, I think that's right, used to thinking about. I think that's correct. Well, that's actually more, that's with the radius set, right? So at the surface of the Earth, so that's not exactly correct. But usually we write as a little g, right? And this is the electromagnetic, the gravitational field, and it's just, big G times m1 divided by r squared times r hat. Okay? So there is this analog, this comparison. The electric field and the gravitational field. They're both fields. And we think of it as something that we can actually interact with. Okay? So we're going to use the superposition principle to define what the electric field is at every point in space, right? It's just the sum of the electric fields due to all the charges in space, okay? Now, don't let me mislead you and make you think that just by simply dividing by the test charge quantity that we've now somehow circumvented all the difficulties of calculating retarded times and stuff like that when charges start to move, when we start to do electrodynamics. That's not the case. It's Maxwell's equation that does that. But we write Maxwell's equations in terms of the fields, the electric field and the magnetic field. And it's through the solution of Maxwell's equations that we calculate for charge distributions what the fields are at every point in space and time. And we don't have to deal with Feynman-Heaviside when we do that, okay? So let me just draw a sample field line. So what might an electric field line look like? We'll find ways to write them, and we'll get into this later. We'll talk about electric field lines, right? And how we characterize them in space, but let me just show you what we can do with them for dynamic purposes, right? So if I pick, say, a point like this and say, here's my test charge, I'm going to put my test charge down right here. All I need to know is what is the value of the field, right? And there will be a force, which is acting, it's just Q, test, times the value of the electric field at that point, okay? And I can use that to figure out what's going to happen to the particle, how it's going to accelerate in that direction, and then we'll be at a new point in space, and we need to know what the field is there, you see? But we are always interacting with the field. We don't have to worry about where the charges are. We have to worry about where the charges are when we calculate the field, but not when we put a particle in the field and make it move, okay? I guess the last thing I'll do is just show you, I'm going to give you a homework assignment where you have some charges and you're going to have to calculate. That's not a nice way to respond. Excitement for homework. Problem sets are exciting. Everybody loves getting problem sets, right? So let's put some charges up here. So this is my test charge here. I'm just going to make an angle theta. So you can see that I've got an electric field acting in this direction at this point, yes? And there's an electric field acting in this direction at this point. From 2. Yes? The total field at this point is the sum of these two electric fields. So electric field 1, the electric field due to charge 1 is just going to be K times Q1 divided by, did I specify this distance? I did not. I'm going to call it Y. Divided by Y squared, and it is in the, I'm just going to call it the Y direction, okay? So we can put down, we've got the X direction, the Y direction, right? What about the electric field due to 2? You can see the things aren't much different here, right? The only real difference you can see so far is that I didn't include another charge here, right? This was a force. I need to put a charge. I need to say what the test charge value is, yes? Q2 over, now what is the distance? It's going to be this distance here, right? Which is what? Well, we've got a triangle which has A and got Y, so what is this length, right? Well, it's just A squared plus Y squared, square rooted, but if I square that, then it's just A squared plus Y squared, right? Did that make sense? Let me just do it like, let me just write it out fully. Squared, and that is in the, I'm going to call it the, this is what I was worried about before. I'm going to call this the R1 direction, and this will be the R2 direction, right? Okay? But that is just equal to K, Q2, over A squared plus Y squared, because when you take the square of a square root, it takes away the square root, right? Yes? So now, though, if I wanted to break it down into X and Y components, right? Again, this is just working with vectors, right? What would I have to do? Well, if I wanted to see what is the field in the Y direction, right? That's going to be the sum of the contributions from this and this in the Y direction, okay? And so from E1, it's pretty simple. It's just K Q1 over Y squared, right? But for this, right, E2, right, what is the contribution in the Y direction? Well, here's our angle theta that we're going to specify, right? We want the Y direction, so we want this times the cosine of theta, right? Cosine is the adjacent over the hypotenuse, right? Yeah. So that's the component we want here. So we'll add to that K Q2 over A squared plus Y squared times the cosine of theta. But what is the cosine of theta? Well, it's Y over the square root of A squared plus Y squared, right? So I can replace cosine of theta with Y squared over the square root of A squared plus Y squared, which I can rewrite as K times Q1 over Y squared plus Q2 over the quantity A squared plus Y squared to the 3/2. Because if you think about it, this squared is A squared plus Y squared. This quantity cubed is this, right? A squared plus Y squared to the 3/2 power, right? So you've seen this several times now. I pointed it out initially, right? Why sometimes you see this cube, right? Because you're going to see it all the time, especially when you simplify things this way. And I don't want you to be confused about it going, I thought I was supposed to have a square of that distance, okay? Okay, so I have to apologize. I made a small algebraic mistake in the lecture. I want to clear it up real quick. I replaced the cosine of theta as Y squared over the square root of A squared plus Y squared, but in fact it's supposed to be Y over the square root of A squared plus Y squared, which will then give us K times Q1 over Y squared plus Q2Y over A squared plus Y squared to the 3/2 power. Sorry about that. And let's see, we can also similarly write, let's get this out of the way, the X component of this, right? There is no contribution to the X component at this test point here from this charge, Q1, right? Because there's no separation in that. But if we look at the contribution from the charge, the electric field from charge 2, right, there is an X component to it, and to find it we need to take this electric field right here times the sine of this sine of theta this time, right? Because it's this component here, right? Sine is the opposite over the hypotenuse, so we'll take this value here, K Q2 over A squared plus Y squared times the sine of theta. But what is the sine of theta? Well, it's just A over the square root of A squared plus Y squared, right? So that's A over the square root of A squared plus Y squared, which we can, of course, write as K Q2A over A squared plus Y squared to the 3/2 power. Yeah, I think that's right. And I probably should have put a negative sign in here since it's pushing, the force is directed in the negative X direction, right? So it should really be a negative sign in here. Should have been throughout. Yeah, that looks good. Last thing I'll mention is in the homework, it almost exclusively, pretty much exclusively works with the following problem. It's one-dimensional. I've got a charge, Q1, located at the origin, so where x is equal to 0. And then I have a charge, Q2, located at x equals a. Right, so this is a distance a away. Okay? And so I'm going to ask you about the electric field in, say, regions over here, and also regions in between them. Okay? And I'm also going to ask you about, well, what if we're in this region over here where x is greater than, right? So in this is the region where x is greater than a. Okay? This is the region where x is greater than 0 but less than a. Okay? So I'll ask you about the electric field in these regions. All right? And then way out here is the region x is much greater than a. Okay? That's very far away. Okay? And so I'm asking you, well, what do you see if you have Q1 and Q2 separated by distance a and you're way far away? What's it going to look like way out there? And so you're going to do some algebra and see if you can answer that question, okay? But it gets a little bit trickier because at some point in the very last problem, I'm going to say, well, you know what? This is minus the magnitude of this. So if this is plus q, this is minus q. We call this a dipole, okay? And I'm going to specifically ask you about a distance which is far away, but not really far away, okay? And it's a little hard to even word it, I guess. But if you get confused about it, right, you can come and ask me, of course. But because, you know, if you get really, really far away, what do you expect this to look like, right? You've got a plus charge and a minus charge, and they're really close to each other. As you get really, really far away, you kind of expect to see that as a 0 charge, right? The plus charge kind of cancels the minus charge, right? And so at a really far distance, you should see nothing. It looks uncharged, right? Kind of like atoms do. Atoms are positive nucleus, positively charged nuclei, and negatively charged electron clouds outside of them, right? If we get really close to an atom, right, it does seem charged, right? We see that outer electron shell, and we'll feel either an attractive or a repulsive force from it. But if we, you know, get far away from it, it just looks like the charges just cancel out, right? So it's a fine line we have to skirt. I want you to look far away, so make the assumption that x is much, much greater than a, but not way out there such that the field is just 0. Right? Let me give you an example. Right? If I said x squared plus 1 over x cubed, okay? And I said, let's look way far away. You'd say, well, it just goes to 0, because when x is large, both of these terms become 0. But I want you to do something like, well, if it's pretty far away, this becomes 0, and maybe this is left over, okay? But when we're really, really far away, then both of them just go to 0, okay? So try to keep that in mind when you work on the homework. And I think that is all I got. Any questions? No? Okay.